All right, I think we can kick this off. So thank you all for coming here. I know this talk is just before lunch, so I'll try to make this worth your time. So today we're going to talk about Uber's journey for scaling OpenSearch, mainly how do we go about building and then operating hundreds of resilient, fault-tolerant, and high-performance cluster. My name is Anurag. I'm a senior software engineer at Search Platform. Today I'll be taking you through the journey of Uber with OpenSearch. So here is the agenda for today, so you know what you're getting into. We'll start by looking at how search evolved for Uber, where we were until last year, and then where we are now. What are the challenges that we have faced through our search journey? Then I'll switch gears and talk a bit about infrastructure at Uber. This will help you actually understand. It'll basically help you understand why we need resiliency and fault tolerance. What are the different failure domains that we have to plan for, and how do we deal with it? Then we'll talk about our deployment, automation, and monitoring. How do we deploy to a single cluster? How do we deploy to hundreds of clusters? And then we'll look at a codification of a deployment pipeline, which will help you understand how to easily replicate a deployment pipeline from one cluster to actually hundreds of clusters. How do you define like a natural order and codification of processes? We'll then switch gears and talk a bit about what sort of failures can arrive when you're trying to deal with a cluster that is deployed across zones, across regions, and a global infra. Finally, we'll touch a bit about horizontal and vertical scaling. This in itself is a huge topic, so I'll just talk about a bit on it in general. And then if time permits, we'll also talk about some of the operational issues that we've faced during the management of our cluster. So starting with the journey of search at Uber. So for the longest time, Uber was actually using a custom search infrastructure. Now this custom search infrastructure was also built on Lucene. So along with it being built on Lucene, it uses something called a Lambda architecture for ingestion. So just a quick show of hands, does anyone know what a Lambda architecture ingestion model is? All right, I see a few hands, so just to make sure that other people are also aligned on this. So a Lambda architecture is it's basically an ingestion model where you use two different type of indexing pipeline. You have a batch ingestion pipeline that is responsible for reading data from a source of truth and then building a batch index on top of it. And then you have a streaming updates so that you can get real-time updates on top of your batch ingestion model. So you have a batch ingestion pipeline that would read data from a source of truth and try to build a Lucene index, and then you would stream any updates that have been built on top of your batch ingestion, so you get real-time access to your indexing data. Now, while this ingestion model works very well for certain Uber workload queries that actually need that basically needs real-time updates to their data. It basically stops us from actually having faster innovations to our search infrastructure. Now the problem with this architecture is that our live ingestion model is a custom one, which means that any new changes that come to Lucene, be it a semantic search, be it a range query support, had some sort of a non-trivial amount of work to actually incorporate into our ingestion model. So starting last year, we started looking at open standard or any open source solution, and for that, OpenSearch was our answer. Now why OpenSearch made sense here? One, because it is open source, so it allows us access to a rich feature set and a vibrant community. Any features that gets developed can be easily incorporated by us and used by any use cases that are within Uber. So with that in mind, let's talk about what are the different use cases that Uber actually has where search comes into picture, and especially OpenSearch. So there are a lot of them, but I'll talk about and try to highlight 5 or 6 of them. So the first and one of the most critical workloads is actually storing observability metrics, right? What this means is that every metrics that is produced within Uber along with all of their tags. So we're talking about billions of document, and each document having thousands of fields, right? So all of this actually gets indexed into OpenSearch, and then we allow users to actually search for metric IDs based on the certain tag values, right? Here we use a bunch of optimizations such as rolling indexes, advanced caching techniques to actually make sure that we meet the scale of serving observability metrics via OpenSearch. The next is being able to search workflows. So what are workflows? So within Uber, we have an in-house workflow orchestration system that basically allows any service or any customer to build job scheduling on top of it. So every workflow along with its metadata going back years and years is actually indexed within OpenSearch, and then we allow people to freely search on these workflows. This is again a very critical workload that actually enables all of Uber's infra to process. The third is something that has been coming up a lot, which is semantic search. There was a talk on this as well. So what is semantic search? So semantic search is where you basically take a huge document, you chuck it into multiple pieces, you compute vector embeddings of it, and then you index it into an index. And then there are users who would take their queries, be it like a string, which would be converted into a query vector, and then you do searches against this. Now, this is a use case that has been coming up a lot when we talk about chatbots, both internal and customer facing. The next, and probably one of the biggest use case that we have at Uber is Eats, which is restaurants, and item search, which is the screenshot that you see on the right. So for every user, there are tens of thousands of restaurants that are available to them, and then within each restaurant, you have hundreds of items. So we allow users to search across these items and restaurant with variable intent. So we are talking about geolocation, we are talking about multiple tags, we are talking about user-based promotion tags that are indexed within your OpenSearch, and then we run search queries on top of it. And then last but not the least, we also have geolocation search. So if you booked Uber to this location, the first time that you search for Sheraton Grand, all the search queries and all the results that are populated within the Uber app are also built on the custom search infrastructure. So apart from this, there are a bunch of other internal use cases that are also powered via our platform. So talking a bit about what sort of scale that we're dealing with. Now keep this in mind that most of the numbers are here have actually come up in the last year, right? Which is when we made the decision to actually move from our custom search infrastructure to the OpenSearch cluster. So we deal with 100+ clusters as of now. For every cluster, you could be looking at 4 to 5 terabyte of index sizes. For every clusters, there would be 150+ nodes in a cluster. And then for a lot of clusters, we would be dealing with 1200 to 1500 peak indexing QPS based on how many number of shards are actually present on your host of a cluster. Okay, so before we start talking about resiliency, right, let's spend some time understanding how does infrastructure really look like at Uber, right? So this is a diagram that tries to paint a 1,000-feet picture of how infrastructure looks like. So the big boxes, the big white 2 boxes that you see are the 2 regions that are within Uber. You have a DCA region and a PHX region. Within those boxes, the smaller gray boxes that you might see are actually availability zones. For every region, you might have about 5 to 6, right? All those small colored boxes that you see are replicas of a stateless service that might be interacting with your storage infra, right? So every time a user uses an app, the calls comes from the Uber edge, which would enter into the Uber network. Then it would be load balanced across one of these regions and then one of these availability zones. Within the region, it would bounce around from one colored box to the other, and then finally it would reach your storage infra. Now this is where your OpenSearch comes into play, right? Now given this region and zonal infra in mind, right, there are different flavors of an OpenSearch cluster that could exist, right? So the first and the basic one would be a zonal OpenSearch cluster. A zonal OpenSearch cluster is where the nodes of your cluster are only within the availability zone where it's deployed, right? Next, you could have a regional cluster. A regional cluster is where your nodes are within a region, but it could be deployed across multiple availability zones. And theoretically, you could also have a global OpenSearch cluster, which means that your nodes are actually deployed across both the region, but that's not what we deal with. So a few things to keep in mind when you look at the picture, right? So the first thing is, like I said, Uber's infra actually deals with regions, multiple availability zones within a region, and then a bunch of storage infrastructure that could either be zonal or regional or global, right? Now when we talk about what sort of latencies that you see, so the thing to keep in mind is that the latencies between the zones within a region are low enough that synchronous communication is efficient between the services, right? But as soon as you try to cross the boundaries of the region, your latency could go for a toss. So theoretically, we'll always deal with regional or zonal infra, never a global infra, although that could be possible as well. Okay, so keeping the infrastructure 1,000 feet view in mind, right? We always have to build our clusters and we always have to build our deployment systems assuming that it can fail at any of these dimensions. So we talked about regions, we talked about zones, we talked about host, right? So the first thing is it may be rare, but your whole region could be down. Now your region could be down because multiple zones in a region could be down or disconnected, or it could be a bad deployment that is trying to affect a whole region, which means that when you're dealing with regional infrastructure, you need to make sure that you have enough redundancy across both regions so that in case of a regional failure, you can actually shift both your indexing and search traffic from one region to the other, right? So you always want to make sure that your regional infrastructure is sufficiently provisioned so that it can handle the traffic from both the regions in a single region, right? So the way we handle this is by actually deploying an active cluster in both the regions. So this is one dimension of failure. The other dimension of failure that you could deal with is a zone being down. Now this is something that actually happens quite often because for Uber, we deal with multiple cloud providers. So you could have a case where a single availability zone is in a different cloud provider, and then another availability zone can be either part of an on-prem infra or a different cloud provider, which means that your zone could lose connectivity to the other zone, which could bring down your cluster, which means that to deal with these scenarios, you always want to make sure that if you're dealing with a regional infrastructure, you have sufficient redundancy across these availability zones so that in the case of failure, no matter what indexes or shards you have, you can always either come out of it as quickly as possible with the least data loss that you can give. So we'll talk about some of the strategies that we employ to actually deal with zonal failures. Okay, last but not the least, host or rack down is something that is pretty common. If you're dealing with cloud providers or if you have an on-prem zone, host or rack down due to networking issue, power issues to the rack itself, or disk corruption is something that we face on a regular basis, which means that we also need to build redundancies across these hosts on racks so that in case of these failures, we can easily come out of it. So yeah, we talked about regional failures, we talked about zonal failures, then we talked about host or rack failures, right? Now we'll try to think what are the different strategies that we can employ for each of these so that if it happens, how do we come out of it? So the first thing I want to touch upon is how do we really handle deployment at Uber, right? So we'll start by understanding how do we do it for just a single cluster, and then we'll try to extend it for hundreds of clusters, right? Now, at the very basics, right, we deal with containers. So a particular OS node is built up of multiple containers, which are the three that you see right here. The first is your OpenSearch container, which would actually host the core code base. Then we have an Nginx proxy that runs on top of every node, which acts as a reverse proxy with its own settings and timeouts. And then for every cluster, we also couple it with a dashboard container that basically allows either admins or users to do any operations on top of it. So given this container model in mind, right, instead of dealing with the OS cluster directly, what we do is we define a concept of goal state. Now, what is a goal state? So a goal state is basically a custom representation of your cluster, right? Now, it could involve your cluster setting. It could involve any resources that are needed for that node, be it your CPUs, your cores, and everything. It could be anything that you want to package to define your cluster. That is your goal state. Think of it as a custom model that helps you define your cluster. For every cluster, we then collect the actual state for the goal state, which means that we have a sidecar that is deployed with every container, which would continuously poll the container to collect the actual state for the goal state that you define. Then we define a drift computing logic, which means that your goal state was supposed to be X, but your actual state is Y. The difference is X minus Y. And for every drift, we define modular workflows that try to modify, which means this becomes a perpetually running loop for every cluster, where you define what is your representation of your cluster, what is the actual value of the representation of your cluster, what is the difference between your goal state and actual state, and what are the things that you have to do to make sure that your goal state converges to your actual state, right? Now, a very basic thing or a very basic example to help you understand this could be changing a cluster setting. So instead of a user directly trying to log into the node or directly trying to deal with the cluster to hit the APIs, we would always define a modular workflow which would be responsible for changing the setting. So instead of people randomly trying to hit APIs, all operation goes via a modular workflow. Now, why a workflow? So a workflow gives you a bunch of things. We can define a common audit process, we can define common security processes, we can define a semaphore that actually allows us to control how many operations can possibly take place on a single cluster, or how many operations are allowed to happen on a single cluster. So everything is conceptualized into a workflow, and then you can use those workflows to build as complex of a logic as you want, right? For example, if you've ever brought a node down to upgrade an OS cluster, you always do a few things. You may be trying to either change a certain setting. Now, these settings could be, for example, you want to disable the allocation of primaries, and then after the node is up, you want to re-enable it, right? So all of these operations in terms of hooks are implemented into a workflow, and these workflows allows us to make the changes. So just to concretize what I talked about, right? So we start with a database container. The database container is where our core OpenSearch code is deployed. Along with the database containers, you have a bunch of sidecar containers, which is the white box that you see on the right. These sidecar containers could be an Nginx proxy, or it could be an OS dashboard plugin. Then we define another sidecar container, which is the technology worker. The technology worker is what is responsible for doing this loop, which is continuously measure the goal state and compute the actual state and compute the drift. So the technology worker is exactly what does the job of continuously polling the database container and finding out what is the drift of goal state and actual state. From the worker, there are certain hooks that goes into another component called a manager. The manager is where we define all the workflows, right? So you have a worker and you have and then you have a manager. Worker that is responsible for ensuring the goal state, collecting the actual state, and manager where the actual execution of workflows happen, right? So keeping this in mind, right, when you're dealing with hundreds of clusters, there are always things that can go wrong, right? There are settings that could be left off. There are certain issues that can happen where your clusters is left in a bad state. So how do you continuously monitor for these issues across hundreds of clusters, right? Now these clusters are critical where even a few seconds of downtime can actually mean that there is a user impact, right? So for that, there is a different component called a controller. Now, a controller is a component that is responsible for continuously monitoring every cluster and then finding out any bad setting, right? And then we get to control what are these bad settings. It could be something as simple as saying that for any production index, we always want to make sure that there are at least 3 replicas, right? So instead of trying to define an alert for it, we would define a continuous monitoring operation where every clusters, every index is monitored, and then every time we find out, and then every time we found out that there is a production index that has replica count less than 3, we would automatically trigger a workflow that would fix it. So by defining a controller loop on all of your clusters, you basically delegate some basic on-call tasks to an automated monitoring system, and then you can define alerts on top of it that actually help you track whether this control loop is actually performing correctly or not, right? So like I said, certain examples of what these controller actions are, it could be auto bumping an index replica, or it could be resetting the cluster allocation enable values that are often shuffled around with when you're dealing with a cluster upgrade process. So now you want to take what you learned for a single cluster and then extend it to hundreds of clusters, right? How do you really deal with zero downtime upgrades for a single cluster versus try to replicate it across hundreds of clusters? So if I talk about a single cluster, I mentioned a point around semaphores, right? So when you're trying to do a rolling upgrade, how do you essentially make sure that there is no other operation that is happening on the cluster that can actually compromise this cluster, right? So this is where workflows come into picture. Instead of trying to bring down the node systematically via logging into the node, we would always define certain workflows that are responsible for bringing down the node, doing certain operations, and then bringing up the node, right? On top of these workflows, we define a semaphore that basically controls how many workflows can actually run at a time on a single cluster, right? So for example, you could say that at a particular point of time, only a single node can be brought down and no more than it. The rest of the points cover some of the basics of how do you really do rolling upgrades. So if you've ever gone through this process, some of this might be obvious. So for example, you always try to upgrade your data node before the master node. You always want to disable your shard allocation for your replicas because you don't want your OpenSearch cluster to waste its resources trying to move replicas when you know that your node is going to be brought up in a few seconds. You want to flush your data before you bring down your node. Similarly, another thing that we want to do is to always promote other replicas to primary. Now, what does this mean? If you know that you're about to bring a node down for an upgrade, and if that node actually contains primaries of a particular shard, you want to make sure that before you bring down a node, another replica on a different node should be made a primary before allowing your workflow to bring down the node, right? So this allows for a zero downtime upgrade for a single cluster. Now let's keep this template in mind and let's think about how do we do it for hundreds of clusters or even more. So first things first, how do you as an on-call actually continue to monitor whether there is an issue with a particular cluster upgrades or not, right? How do you build the monitoring and an automated recovery process? Now, at least for us at Uber, for every production cluster that gets created, we define about 50 to 60 alerts. A screenshot of it is towards the right, and there are probably more. It could be as simple as actually computing the zonal latency for a cluster, which means what sort of latency are we seeing in a single availability zone, then similar to that, a regional latency, then trying to find out whether your cluster is either in a red state or in a yellow state for an extended duration of a time, or it could be that your nodes are in a random state, right? So you define all of these alerts, and then you define a callback that if any of these alerts get triggered, I want to pause my rollout right then and there and alert an on-call that you need to take a look, something is wrong with your upgrade, right? So this way we can basically trigger a pipeline and then continue to monitor in an automated way if something happens to your cluster. So once you've defined something for a single cluster, to do it across hundreds of clusters, we use a concept of cluster release pipeline, right? So a cluster release pipeline is a fancy word for a codification of a natural order of an upgrade for hundreds of clusters, right? Now when you deal with hundreds of clusters, you know that not every cluster is the same criticality, right? You could have an expendable staging clusters versus you would always have a production cluster. Within those clusters, you would have different criticality of the data, right? So the first thing that we do is we start by identifying what these clusters are. Every cluster that gets created goes through a metadata process where it would be tagged with certain attribute that would help us identify what is the criticality of the data. Is it a user staging cluster versus whether it's a production cluster? We then define a data tier. A data tier tells us basically how critical is the data within the cluster, which means that if the cluster is not available, what is the impact to the user? So we have a process where the tier values could be 5, 4, 3, 2, 1, and 0. 5 being it is an expendable cluster used only in staging, and 0 being it is a critical cluster that can actually bring Uber down, or it could impact Uber customers directly, right? We then define for every tier a natural ordering of use cases, again using the tags. Then we define a region ordering, which means you always want to upgrade your DCA cluster before you do PHX cluster, so that if there's any issue with a single region, you always have the ability to move all the traffic to your other region. Then one thing that we touched upon is that you want to define rollback alerts, right? So every alert that I showed you in the last screen actually acts as a hook. So anytime any of those alerts trigger, it would pause the pipeline, it would alert the on-call that, hey, something has gone wrong with your upgrade process, please take a look. Then you want to define a soak, which means you want to give enough time after every tier upgrade so that your alert can actually soak in and trigger if there is an issue, right? And then before you move on to your final critical clusters, we introduce a manual acknowledgement. So like I said, a cluster release pipeline on the right is basically a codification of a natural order of things or a natural order of clusters that you want to proceed. And within the clusters, you also want to define what is the first region that you want to deploy in, what is the first zone that you want to deploy in, what are the alerts that you want to monitor for every step before moving on to the next step. Okay, so let's switch gears for a second, right? We talked about different failure domains that an OpenSearch cluster could see. We talked about a regional failure, a zonal failure, and a host failure. The next two slides specifically will talk about how can you handle zone failures for your clusters, right? What are the things that an OpenSearch cluster makes available to us to handle this? So for this, I will introduce a concept called isolation groups, right? So this is a concept within Uber's infrastructure system where we define or assign a logical attribute to a node, right? Now for us, this value is just 1, 2, or 3, right? This is just a random label that we assign to every node in the cluster, right? Now what we do with the label is where it gets interesting, right? So let's assume that you have a cluster on your right that contains 8 nodes, 8 data nodes. You would first want to assign it an isolation group value 1, 2, and 3. Let's say there are 3 nodes in your first isolation group, there are 2 nodes in your second isolation group, and there are 3 nodes in your third isolation group. Now, to assign these isolation group, I will define 2 constraints. The first constraint is that 2 or more isolation groups may never be present in the same zone, or vice versa. No zone should ever have 2 isolation groups. So that's the first constraint. The second constraint is that isolation group sizes must be balanced with a max queue of 1 node. Now what this means is that you want to assign your isolation groups to a node such that these 2 constraints are always met. So for example, in a cluster of 8 nodes, what you'll see in the diagram is that 3 nodes get assigned to isolation group 1, 2 to 2, and 3 to 3, which means the skew is never greater than 1. If I try to assign a new node in an isolation group, I'll never add it to isolation group 3 or isolation group 1, because that means the skew of the node would increase by 1. The second constraint you want to make sure is that for every isolation group, no zone should ever have an intersection, which holds true, right? Now once you've made sure that these 2 rules are followed and the isolation groups are assigned, what starts happening is that any time a single zone is down, you can be sure that you will never lose more than 33.3% of your cluster. That's one. But there is still a problem with that. The problem could be that maybe these data nodes actually host more primary shards than necessary, which can actually bring down your index if one of the zone goes down, right? So keeping this isolation group concept in mind, what do we do next? So for those of you that might not know, OpenSearch has a concept of shard allocation awareness, right? Again, it's a fancy term for letting OpenSearch know whether there is an attribute for a node that an OpenSearch cluster should be looking at before distributing the shards to different node. Now, it could basically be any attribute for your node. It could be a host name, it could be a rack name, it could be a zone name. So depending on what do you want to build resiliency against, it could be any of these attributes. So for us, since in the last slide we introduced a concept of isolation group and made sure that the 2 constraints that we talked about actually holds true, what we're going to do is we're going to set the awareness attribute as the isolation group, which is this new attribute that we introduced, and then let OpenSearch know what are the different values of the isolation group, which is 1, 2, or 3, or 0, 1, or 2. So combined with the last constraint and setting the shard allocation awareness, we have now made sure that at any point of time, if an availability zone goes down, none of the shards of the indexes will ever lose more than 33.3% of it, which means that any replica has the enough quorum to actually be promoted, right? Next, to even strengthen this concept, right? Every few months, we have a concept of a zone or a node failure resiliency drills. What we do here is basically try to bring a node down by actually disconnecting it from the rest of the infrastructure and see how your OpenSearch cluster behaves, right? It is sort of a chaos testing for your zone networking. And this helps us ensure that at any point of time, if your zone is down, there is always enough replicas for every index's shard for it to sustain failure. All right, so I'll quickly touch upon the next set of slides, which talks about scaling. Again, scaling in itself is a huge topic, so I'll talk at a very high level what sort of scaling we have in place. It becomes more of an art than an actual science in a lot of use cases where you have to deal with a lot of issues with the unpredictability of the traffic, and how do you balance your cost and your performance while making sure that your clusters are not over provisioned all the time, right? So again, when we talk about scaling, we always talk about either vertical scaling or horizontal scaling. Vertical scaling is throwing more resources to every node. Horizontal scaling is adding more nodes to your mix. So when we talk about vertical scaling, we do vertical scaling for every node in the cluster for two stuff. One is your CPU cores, the other is your disk. Both of the CPU is actually a predictive scaling, but not a reactive scaling, what that means is that for every node of the cluster, we start by assigning a dedicated number of cores, which should handle all of its average traffic. And then we define a shared buffer for every node where it can break into, right, every time the amount of traffic increases, right? If you look at the diagram to the right, that should give you an idea of how vertical scaling takes place. So for every node, we are continuously monitoring what is the current usage of CPU cores, what is the current allocation of the CPU cores, what was the last 30-day prediction, I mean, based on the last 30-day window, how much extra CPU cores would a particular node need? And if it is more than that, we then go on to define a delta, which says how many days would it take for one node to actually move from X CPU cores to Y CPU cores over Z days, right? So based on certain rules, based on certain prediction patterns, we let our nodes scale up while ensuring that at any point of time there is at least a minimum baseline CPU cores and disk that is available to all of our nodes in the cluster. Now these rules differ for production instances and staging instances. For some of the critical clusters, we would never want to automatically downscale, but we can always upscale. So based on certain deltas, based on how critical your use case is, this diagram could be different. But what you see here works for most of the standard use cases that we have within Uber. So similar to vertical scaling, we also have horizontal scaling. Again, for us, horizontal scaling actually happens on disk, which means that for every node, we define a minimum and a maximum data size of a node. Below a minimum data size of a node, we would try to remove a node and let OpenSearch rebalance its shard. Beyond the maximum data size on a node, we will add another node with the average data size of the rest of the cluster, and again, let OpenSearch move these shards. So horizontal scaling, vertical scaling works together to make sure that we are not always highly over-provisioned to handle all of our peak traffic, while also making sure that there are no performance degradations for any normal increases in traffic. So we implemented this about a year ago. Combining the horizontal scaling and vertical scaling, we've actually seen about $1 million per year in cost savings due to the rollout of vertical scaling and horizontal scaling. Again, this is owing to the fact that previously you would always try to over-provision your cluster to handle your peak traffic, because when you're dealing with Uber traffic, they have seasonality. There are certain days in the year, there are certain months in the year where you would have a very high number of eats order versus rides order and so on. Okay. Now, last but not the least, before I wrap up, I also wanted to talk about an interesting operational issues that we faced while trying to manage a cluster that is deployed across multiple availability zones. So Okay. So before I go into that, how many of you know about the concept of leader checker, follower checkers? Is this something that you've heard in the context of an OpenSearch cluster? Okay, so for those of you that might not know, OpenSearch uses a concept of a leader checker and a follower checker to ensure that your cluster is working perfectly at all times, and it can automatically remove a wrong data node if there's an issue. Now, very simply put, leader checker is a piece of code that is deployed on every non-follower, on every non-leader node that would try to ping the leader and see whether it's healthy. And follower checker is a piece of code that is deployed on your cluster manager primary node, which would try to ping every other node to see whether it's healthy, right? Now, the way OpenSearch finds out that there is something wrong with one of the nodes is that it would wait for an n number of consecutive failures, where n is 3 by default, for a source node to assume that there is some issue with a target node. Now, when you're dealing with networking issues, right, a lot of times you would never have a complete network partition, but you would have symptoms where your network is degraded due to partial drops in packets. And we dealt with a very similar case where your leader and follower checker would fail one time, and then it would basically pass, and then it would fail again 2 times, and then it would pass again, which means your OpenSearch cluster was never able to detect a partial network degradation in an availability zone. So this led us to actually build an out-of-the-box solution where instead of relying on the OpenSearch cluster's failures, we built a monitoring on a moving window of the leader checker and follower checker, which means that in a few seconds, if the sum of your leader checker failures or your follower checker failures has increased a certain threshold, we would again trigger a workflow using the controller that would automatically either move the master to a different node, or it would move a primary shard to a different node to automatically mitigate any partial network degradations in an availability zone. So this was an example of an out-of-the-box solution that we did that has actually been useful for us in a lot of these past incidents without an on-call being present. There are obviously more, but my time is up, and that's about it. If you guys have any questions, happy to take them. Yeah. Mm-hmm.
Mentioned about the auto-scaling.
Right.
The auto-scaling, you said it's about the seasonality that you're able to manage.
Mm-hmm.
What happens when you have a sudden burst? How do you manage that?
Right. So the burst itself is managed in 2 cases. So again, when we talk about scaling, we talk about reactive scaling and we talk about predictive scaling. Predictive scaling comes into picture when you are dealing with natural increases of traffic, and reactive scaling comes into pictures when you're dealing with certain bursts of traffic that wasn't expected by the product team. Predictive scaling helps us deal with any of these natural increase of traffic over time. For any burst of traffic, if it is predictable from the product team, they would reach out to us and we would automatically over provision it. For certain cases, we always define a buffer of cores that at any point of time a cluster can break into to handle any burst of traffic. But beyond that, it will always be an issue for any of the clusters. So that is where the on-call comes into play and would have to do certain manual operations to handle it.
So when you react, do you have a time window?
Yes, yes. So the time window is basically looking at the past 30 days prediction and then scaling it to a threshold in the next 7 days. Yeah, but again, the number 30 and 7 could be different for different clusters, but that's what works for most of our clusters. All right, if there are any questions, I'll be around. Happy to chat with anyone. Thank you.